Hello everyone, welcome back to another Geostats lecture video. And in this lecture video, I want to talk about the lagged means, and the lagged means plot. So what we're going to do before we do anything else is get our data set squared away. So what we're going to end up doing is we're going to end up taking the same steps that we did in the previous video of calculating that neighborhood weights, the neighbor matrix, and then the spatial weights matrix. So we're going to build off of that. So what I'm going to do is I'm going to copy the 5 lines of code that are responsible for that. So that's the first 3 up here. If you don't have this code in front of you, take a second to type it out. We're going to load the data, generate connectivity, and then convert that connectivity to the spatial weights matrix. So at this point, if you don't have these 5 lines of code and you're trying to follow along, pause the video until you get caught up. I'm going to run these. Okay. So we now have our spatial weights matrix. So in order to actually calculate lagged means, we're going to be using another function from the spdep package. Specifically, we're going to be using the function lag.listw. Okay, so the lag.listw function is, again, using the listw, so that's our spatial weights matrix, compute the lag vector vx. So this lag vector, that is just a fancy way of saying calculate the mean of all of the neighboring objects. And so what it takes in as parameters is the x, so this is our spatial weights matrix, and the variable, or var, this is the actual variable that we want to use to calculate that average, right? This is that value that we were talking about in the conceptual videos. So let's go ahead and quickly do this. Again, we're going to do a rook case and a queen case. So what we're going to do is we're going to set up our lagged means. So to do that, we're going to have rook underscore lag, and we're going to set that equal to spdep, which again is the package. And then we're going to do the lag.listw. So again, x parameter, this is that spatial weights matrix. So we're going to use the rook case first. Okay. And then the var, this is going to be the variable that we're interested in. So again, I'm going to be using the %rural from the Georgia dataset. So this is going to be Georgia at data $, and then %rural. Okay. So if we run that, let's take a look at what we got before we generate the Queen's case. So what we have is we have a list of, or a vector, I should say. We have a vector of values. So these values are the lagged means for that particular neighborhood data structure. Okay. So let's go ahead really quickly and calculate the Queen's case. Again, right, spdep, and then we're going to call lag.listw. Again, x is the spatial weights matrix, which in this case we're using the Queen spatial weights matrix. And then our variable in this case is also going to be the Georgia at data $%bachelor, or sorry, %rural. Okay, so we're going to run that. And then what I want to do, just to show you that it does actually change a couple of the values, is I just want to quickly go down here and I want to type in queen underscore lag. And I want to set this up so we can look at them sort of side by side. So you can see here that most of these values are actually the same. But there are a few, for example, 16 here. Actually, this is a different size. Never mind, we can't do that. That comparison does not work directly like that. But there are a few in here that are different. Again, because if you go back to the previous video and you look at the connectivity for the spatial weights matrix, there were a few that were different. So this does actually affect the results. Okay, so now we have the lagged means. Okay, so let's go ahead and generate our plot. Actually, you know what? No, let's before we do that, let's actually visualize our lagged means. I actually need to install one more package because I did not install already. That's the tmap library so that we can do some quick plotting. Okay. So what I want to do is I want to join lagged means back to the data. And to do that, we're going to take our GEOR Georgia data set at data $. I'm going to call this variable rook_lag. So this is going to create a new column in the data frame called rook_lag. I'm going to set this equal to rook_lag. All right. So now our lag data for the rook's case is included in the Georgia data set. I'm just going to copy this over and I'm going to make the queen one as well. So queen lag is now going into queen lag. Okay, so we now have those data in the data frame. So now what we can do is we can call a tmap, we can call tm_shape, and we can call in the GEOR-GI dataset. Okay, and we can add in a tm_polygons, and we're going to have color be driven by rook_lag. And so I'm going to run this down here. I'm just going to call tmap. Oops, I always forget you have to put the name in quotes. Let's try that again. There we go. So this is the rook lag. So what this is showing you, where the areas are high, that means there is generally a higher level of autocorrelation. Where the values are low, there's generally a cold spot. Right? Where they're high, that means that the neighboring regions are also high. So basically what you're looking for are regions of extreme values in the high and extreme values in the low. Because what we would hope to see if there was no autocorrelation is that everything would just be sort of in the middle. Right? We can do the same thing for the queen case. GEOR-GIA plus tm_polygons call equals queen_lag. Right. And so now if we call tmap queen, right, see, mostly it's the same sort of scenario. So this is how we visualize the actual lag values. And again, what you're looking for are areas of high values and areas of low values, because that generally means that you have autocorrelation. So let's talk about actually making the lag plot. So what we're going to do to make the lag means plot is we're actually going to plot, and I'm using the generic plot function here instead of ggplot. X equals, so the x-axis is going to be our Georgia at data $%rural. Right, that's what we would expect, or that's what we normally have. And then we're going to plot that against, on the y-axis, our Georgia at data $ rook lag. Right? So if we plot that, and then we call the plot, right, we can already kind of see that there isn't really a trend here, which is a good sign. But what we want to do to sort of confirm that is we want to add an ab line of a equals 0 and b equals 1. So this is going to plot a 1-to-1 line. It's probably not going to like what I just did. There we go. All right, so this is the 1-to-1 line. So if we had a very high level of spatial autocorrelation, we would expect the values to fall along this 1-to-1 line, right? Because they don't, right? You see they're not really falling along this 1-to-1 line. That's a good indication that overall this data set does not exhibit spatial autocorrelation. Right? Again, just to reiterate here, what we've done is we've basically plotted the values that we got compared to the lag, and then we used the 1-to-1 line as our sort of worst case, right? If everything fell along the 1-to-1 line, that would mean that we had a fairly high level of spatial autocorrelation. So the farther you get away from that, the less autocorrelation you likely have in your data set. Hopefully that made sense. And then just to sort of recap the concept, we can do the same thing here with our queen. Georgia at data $%rural mapped against our Georgia at data $queen lag. Right. And then we can add in the 1-to-1 line as well. Okay, so hopefully that makes sense. Again, this is the this is how you go about making that lag means, calculating the lag means and making the lag mean plot. I know there's a little bit more code here, but hopefully everything makes sense. And as always, please reach out. Thank you.